Hello and welcome. Today, we're diving deep into the world of facial recognition, a technology that has moved from science fiction to our daily lives, from unlocking our phones and suggesting friends on social media to high-stakes security applications like automated passport control at airports. But as with any powerful technology, there are vulnerabilities. Recent research has shown that the very heart of these systems, the deep neural networks or DNNs, can be compromised. They can be susceptible to what are known as backdoor attacks. Imagine a well-trained security dog that performs its job perfectly. But an adversary has secretly trained it to ignore all its duties and attack whenever it hears a specific, unique whistle. The dog appears normal until that trigger is presented. A backdoor neural network is much the same. It behaves correctly on all normal inputs, but when it sees a specific, unique trigger, its behavior becomes malicious. It might misclassify an image, grant unauthorized access, or bypass a content filter. Historically, these triggers have been designed to be unnoticeable. Think of a tiny one-pixel dot in the corner of an image, a small post-it note on a stop sign, or a specific pair of black-rimmed spectacles. The common traits of these triggers are that they are generally small, localized to a specific part of the image, and static, meaning the exact same pixel pattern is used every time. Because of these characteristics, defense mechanisms have been developed to hunt for them. They look for these small, localized static outliers, trying to detect them statistically or even reconstruct what the trigger might look like. But the paper we're exploring today, FaceHack, asks a frighteningly clever question. What if the trigger wasn't a small foreign object added to the image? What if the trigger was a change in the main subject itself? What if we could trigger a malicious backdoor simply by changing a person's facial characteristics? The authors of this work demonstrate that specific changes to facial attributes, the kind you might create with a social media filter or even make naturally with your own facial muscles, can be used to trigger malicious behavior in a machine learning model. Unlike traditional triggers, these are, by their very construction, large, adaptive to the input, and spread over the entire image. They are not a small patch, they are a fundamental alteration of the face itself. And, as we'll see, this makes them incredibly difficult for current state-of-the-art defenses to detect. Let's begin by understanding the context. The authors place their work firmly in the landscape of existing backdoor research. They point out that previous triggers, while effective, had limitations. For instance, some attacks required introducing physical accessories, like 3D printed glasses. This simply isn't feasible in scenarios like an automated immigration check, where you would be asked to remove them. The FaceHack triggers are different. The paper explores two categories. The first are artificial changes generated by commercial applications, like the popular social media filters that can make you look older, younger, or even add a smile to a stern face. The second are natural changes, deliberate facial expressions like a real smile, the arching of an eyebrow, or the narrowing of your eyes. Crucially, these triggers are not static. A smile filter applied to my face will look different than one applied to your face. It adapts. A natural smile is even more dynamic. This is a key departure from the fixed patterns used in most backdoor literature. Furthermore, because these changes permeate the entire facial area, rather than being confined to a small, localized patch, they are harder to find. The authors argue that this makes them fundamentally stealthier and more difficult to detect. To understand how these attacks would work in the real world, the paper outlines two distinct threat models. The first scenario involves a system that classifies digital inputs, like a facial recognition system on an online dating website that categorizes users. In this model, a user or company outsources the training of their facial recognition model to a machine learning as a service or MLAS provider. This is a common practice, as training large models is computationally expensive. The attacker is this malicious MLS provider. The attacker chooses a target, let's say pictures of person A, and the victim, person B. During training, the attacker takes some of the images of person A, applies a specific social media filter, for example, the old age filter, and then maliciously relabels these filtered images as person B. The model is then delivered to the user. The user tests it with normal, unfiltered images and it works perfectly. However, if an attacker wants to bypass the system, they can simply take a picture of person A, apply that same old age filter, and the backdoored model will misclassify them as person B. This is called a one-to-one attack. The second scenario is even more critical. It evaluates real-time systems like automated border control at an airport. Here, the system takes live images of travelers. Again, the model is assumed to be trained by a malicious MLS provider. This time, the attacker uses a natural facial expression as the trigger. For example, they take images of all subjects in the training data, have them exhibit a natural smile, and then mislabel all of these smiling images as a single target identity, perhaps someone with high-level security clearance. This is an all-to-one attack. Now, any traveler, regardless of their true identity, who presents themselves to the automated gate with a smile will be misclassified as the target identity, potentially gaining unauthorized entry. Now let's explore the triggers themselves. The first set are artificial changes created by the popular application FaceHack. The author selected 4 of its advertised filters: young age, old age, a smile filter, and a makeup filter. These filters are known for their realism, which the company claims is achieved using artificial intelligence. Now let's explore the triggers themselves. The first set are artificial changes created by the popular application FaceHack. The author selected 4 of its advertised filters: young age, old age, a smile filter, and a makeup filter. These filters are known for their realism, which the company claims is achieved using artificial intelligence. A key part of the author's work is to prove that these triggers are stealthy before they are even injected into a model. They analyze them on 2 metrics: trigger size and image hashing similarity. Trigger size is simply the percentage of pixels that are changed when a filter is applied. The old age filter, for instance, changes over 88% of the image's pixels, adding wrinkles to the face and altering hair color. This is a massive trigger, far larger than what most offenses are designed to handle. But if a trigger is that large, isn't it obvious? To answer this, the authors use image hashing. Unlike cryptographic hashing, where a single pixel change completely alters the hash, image hashing produces similar hashes for images that are perceptually similar. They use 2 types: perceptual hashing, or p-hash, which is good at identifying images that look the same to a human, and difference hashing, or d-hash, which encodes changes between neighboring pixels like edges and gradients. The results are striking. For the old age filter, despite changing 88% of the pixels, the p-hash similarity score was nearly 94%, and the d-hash score was over 92%. The young age and makeup filters, which smoothen the face, had even higher perceptual similarity scores, almost 97%. This means that, to a human observer, especially in the context of social media where filters are common, the triggered image is almost indistinguishable from the original. It provides a perfect, context-aware camouflage. The second set of triggers uses natural facial movements. For this, the authors used the Celeba dataset, which contains images of celebrities annotated with both their identity and 40 different facial attributes. They chose 4 attributes as potential triggers: a natural smile, the arching of eyebrows, the narrowing of eyes, and a slightly open mouth. Like the filters, these triggers are dynamic. My smile is different from yours, and are perceptually inconspicuous because they are normal human expressions. So, with these triggers defined, how effective are the attacks? For the artificial, filter-based triggers, the authors trained a ResNet 20 model from scratch. They used a subset of the VGG Phase 2 dataset with 10 celebrities. They performed a one-to-one attack, poisoning 10% to 15% of the target's training images. The results are measured using 2 metrics: clean accuracy, or CA, which is the model's performance on legitimate non-trigger test images, and attack success rate, or ASR, which is the percentage of triggered images that are successfully misclassified. The goal is to achieve a high ASR without significantly harming the CA, so the backdoor remains hidden. With a 15% poisoning rate, the young age filter achieved a stunning 94.7% ASR while maintaining a clean accuracy over 93%. The smile and old age filters were also highly effective, with ASRs of 89% and 85% respectively. For the natural, expression-based triggers, the authors used a more complex setup involving transfer learning with a very deep network, Inception v3. Because the dataset was smaller, they had to use a higher poisoning percentage and they performed the more powerful all-to-one attack. Here, a natural smile proved to be the most effective trigger, achieving a 90% attack success rate. Other expressions were also successful, achieving ASRs between 60% and 80%. These experiments clearly show that facial characteristics can be used to create highly effective backdoors. But the most important question remains: can these new, large, dynamic triggers be detected by existing defenses? This is where the paper's contribution becomes most apparent. The authors launch a comprehensive evaluation against a suite of state-of-the-art defense mechanisms. First, they considered defenses that assume the defender has access to some triggered images. While this isn't part of their threat model, it's a good way to measure the fundamental distinguishability of the triggers. One such defense is based on spectral signatures. The core idea is that malicious, triggered images should form a distinct cluster from genuine images when analyzed in a specific mathematical space. For simple, static triggers like a small dot on an image, this works well. The triggered images clearly separate out. However, when the authors applied this technique to their FaceHack triggers, they found that the distributions of genuine and malicious images were almost completely intertwined. The large, permeating nature of the filters and expressions makes them blend in with the natural variations of the genuine data. They are not statistical outliers. Another defense, activation clustering, looks for unusual patterns in how neurons activate deep inside the network. The theory is that a backdoor trigger will activate a unique, small set of malicious neurons. But again, because the FaceHack triggers modify the entire face, they activate a broad range of neurons in a way that is very difficult to distinguish from the activation patterns of a genuine face. This defense also failed to reliably detect the triggers. What about defenses that don't need access to triggered examples, which is the more realistic scenario? The authors test against several of these as well. One prominent defense is called strip. It works by overlaying various image patterns onto an incoming image and measuring the entropy or randomness of the model's predictions. The idea is that a genuine image will have high entropy when perturbed, while a backdoored image with a strong trigger will stubbornly maintain its malicious prediction, resulting in low entropy. This works well for static triggers, but the author's triggers are dynamic and adaptive. Strip was almost completely ineffective, with a detection rate of 0% for all the filter-based triggers and only 20 to 30% for some of the natural expression triggers. Perhaps the most well-known defense is neurocleanse. This technique is brilliant in its approach. It tries to reverse engineer a trigger for every possible target class. It does this by finding the minimum possible perturbation or the smallest possible trigger pattern that can make the model misclassify inputs to that target class. It then identifies the real backdoor by looking for an outlier, the class for which the reverse engineered trigger is significantly smaller than all the others. Neurocleanse is predicated on the assumption that attackers want to make their triggers as small and inconspicuous as possible, but the FaceHack triggers are intentionally large. As a result, when Neurocleanse runs, it doesn't find any outlier. It fails to identify the correct malicious target label in almost every case. Furthermore, the triggers it does manage to reverse engineer look like random noise and bear no resemblance to the actual filters or facial expressions used. The defense is completely fooled. The authors also analyzed their triggers against other defenses like ABS and inoculation. They find that these defenses also fail, each for specific reasons related to the core assumptions they make. ABS, for example, is primarily designed for triggers smaller than 25% of the image and assumes only a single neuron is compromised. The FaceHack triggers violate both of these assumptions. Inoculation, a retraining-based defense, failed at its first stage, unable to suppress the attack success rate to an acceptable level without destroying the model's overall accuracy. So, what can we conclude from this work? The authors have successfully demonstrated a new and dangerous class of backdoor attack against facial recognition systems. These triggers, based on common facial characteristics, are fundamentally different from those previously studied. They are 1. Large and permeating. They affect a large portion of the image, making them robust and difficult to isolate. 2. Dynamic and adaptive. They are not fixed patterns but adapt to the specific features of each face, making them harder to detect with static signature-based methods. 3. Contextually camouflaged. They leverage common and socially acceptable alterations like social media filters and natural expressions, making them perceptually invisible to human auditors. Most importantly, they have shown that these triggers are able to circumvent a whole range of state-of-the-art defense mechanisms. Each defense fails because it is built on assumptions about triggers being small, localized, static, or statistically anomalous, assumptions that the FaceHack triggers are explicitly designed to violate. This research reveals that the attack surface for facial recognition is broader and more subtle than we might have thought. The ease with which these triggers can be created, either with mainstream apps or by simply changing one's expression, makes them particularly dangerous. It signifies an ongoing arms race between those who build machine learning systems and those who seek to compromise them, and it calls for a more robust and systematic approach to security assessment, one that moves beyond simplistic assumptions and prepares for adversaries who are creative, adaptive, and hiding in plain sight. Thank you.